Morning. There are no spots.
Yes, there is. I'm gonna put my name on a sticky note.
Tiana, did you give me that your notebook yesterday? Who did you give that your notebook to yesterday? Jeez, why do you guys not? What do you need a notebook for?
I don't need a notebook for PFL. I can do it all on the computer. No. At PFL, so I can try my second hour there. We just steal all of that camera.
Hey, leave my scratch paper alone.
You're a notebook then.
Hey, I am not the notebook supplier for the 1992 Olympic team, so knock it off. You're lucky that I happen to have some.
When are you gonna run out one?
When they're gone.
What has swimming to do anything with a notebook? Nice catch.
Good morning, ladies and gentlemen. How are we doing today? Wonderful, 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 ladies and gentlemen. Take out your computers. You're going to need them. Okay? And start thinking about the question of the day today. Would you rather be driven to and from everywhere by your mom for the rest of your life, or have to take a sibling, a younger cousin, some stranger that you're responsible for everywhere you go for the rest of your life?
What happens if your mom dies? Oh, then you're watching.
She's going to live forever in this one. Or outlive you because you're going to die of embarrassment from your mom dropping you off everywhere.
But my mom doesn't scream or anything like that.
I didn't say she does. Then this should be an easy choice for you. Oh, lefty, ladies and gentlemen. Let's see who's here today. Why do the righties get all of the credit all of the time? No, Alexa.
See, so that desk is great for you.
No. No, Brianna. Amen.
Mr. Burns, how early do you get here?
6 a.m.
That's too early.
No, just the right time. Just the right time. How do I know? Because I arrive at that time. So it's just the right time. All right, ladies and gentlemen, here we go. Put your phones away, put your headphones away. By the way, if your phone falls out of your pocket onto the ground, it goes into there. So make sure it's somewhere where it will not fall out of your pocket onto the ground. Make sure it is somewhere where I will not see it. Make sure it is somewhere where you will not be tempted to use it. Okay? Oh, lefty, ladies and gentlemen. Here we go. So our question of the day is this, ladies and gentlemen. Would you rather be driven around to and from everywhere by your mom for the rest of your life? Or would you have to take a younger sibling, a younger cousin, or just some random young stranger with you everywhere you go? Which one? Christopher, which one? You'd be driven by your mom? Pull up at the movie theater, or go on a date with a girl and your mom drives you, that's okay? Okay, cool. That's awesome. Ethan?
I'll take my sibling everywhere for the rest of my life.
Everywhere for the rest of your life. So when you go on a date, you're going to bring your sibling with you?
Well, if he has the gas money, sure.
No, that has nothing to do with the question. You have to take them with you everywhere you go for the rest of your life.
I'd be different about my mom.
For the rest of your life?
Yes, sir.
Okay. 30-year-old person going to work in the morning being dropped off by his mother. Okay, all right. Mariana, what are you thinking?
My mom.
Mom? Okay. All right. Faith? Sibling?
Yeah.
An annoying younger sibling?
Yeah, they're like pretty.
Oh, okay. All right, Kiana. Your mom?
Yeah.
Really? Your mom?
Yeah.
Okay.
Yeah,
Okay. I can understand. Hey, quick, wave into the crowd that's all late too, and get in here. All right, Lucy, which one do you want? Mom? Easier than having a younger, annoying person around with you? Okay. Plus, it just says that you have to be driven everywhere by your mom, as opposed to you have to take your sibling with you everywhere for the rest of your life. So maybe you have your mom drop you off 5 miles from the movie theater where you're meeting somebody. I don't know. Jaslyn, what are you thinking?
My sibling.
Sibling, okay? Sibling, go for the sympathy, you know? Oh, I got to bring my sibling with me because, you know, they have no life, they have nothing to do, and I have to take them with me.
Well, my older sister doesn't have a life. She always takes me everywhere.
Really? Well, that's nice. So are you the third wheel?
No. She
No?
doesn't have a boyfriend.
Okay, so you're just the second wheel.
No.
Well, there's two of you, right?
She can be the second wheel.
Oh, yeah, but she's taking you.
Yeah, but...
So that makes her the first wheel. You're the second wheel. Nice try, though. Nice try, though. Victoria, what are you thinking?
I don't know because
Victoria, put away the food.
I'm hungry.
I
I
understand
didn't get
that.
here until 7:15.
And you can eat at 8:41.
Okay. Well, for my little brother, I was thinking you could just shove him in the back seat, give him a video game. But with my mom, she doesn't embarrass me, so it's a 50-50. I don't
So
know.
which 50 are you going with?
Probably take my little brother with me everywhere because you can just shove him in the back seat and give him a video game. And
Okay.
he's good to go.
Okay. Okay. Until he's not, but all right. Okay. Brianna, your mom? Okay. All right. Zoe?
My mom.
Your mom? Okay. Okay. Zoe, you said this was easy, though, because you don't have a younger sibling.
Right.
So you'd have to take some random person with you. Okay, Alex, would you rather be driven everywhere for the rest of your life by your mom, or would you rather have to take a younger sibling with you everywhere you go? Sibling? Even though your mom could just drop you off and then go away, you'd take a younger sibling with you out on a date. Okay, all right, fair enough. I understand. Alexa, what are you thinking? Your mom? Okay, all right, just drop you off and then she leaves. All right, all right, all right, Kevin.
My mom, because she wouldn't understand what we're going to have a conversation with, like a language barrier.
Oh, they don't go away.
Wait a minute. What was that now? Your mom, because why?
Because we have like a language barrier, so like.
Victoria, seriously, you can't eat in here. Okay? Well, I'm sorry, but this is a science room. Okay? Okay, so your mom, because you figure she wouldn't understand everything anyway.
Yeah.
Okay, all right, all right. Helen, what are you thinking?
Probably my mom.
Probably your mom? Okay, okay. All right. Who did I miss? Did I miss anybody? Christian? I noticed you were shoving your hand up there to go, oh, you missed me, Mr. Brand. You missed me. Which one?
My mom.
Your mom? Okay. At least you got a built-in ride then, right? Okay. Well, since I was a younger sibling, ladies and gentlemen, I don't think I would take a younger sibling with me because I was annoying to my brother and sister. That would have been terrible. So, and I wouldn't actually have to worry about the first part either because my mom could never drive. So, but now that I think about it, if she had to drive me everywhere, I would take a younger sibling with me because it would be a better chance of me being alive when I get there. Because I think my mom driving would have been a very scary thing. A very scary thing. Because she used to wear out the floorboard on the passenger side, always trying to brake when my dad drove. So I could only imagine how she would have been driving actually down the road. We would have been going up to when we got up to 30 miles an hour, she would slam on the brakes. So I would probably have to take a younger sibling with me because they might be just as annoying as I was, and that would be just fair for my brother and sister anyway. So, all right, ladies and gentlemen, today we got a number of things to do. Now, here's the other thing that I'm going to tell you. The things that we have been working on, ladies and gentlemen, are going to be the things that are on your quiz on this Friday. So your quiz is going to basically be on energy. So yesterday we started talking about some energy things. So open up your EISN, ladies and gentlemen, and let's take a look at a couple things that are in there.
Don't
All right.
like food.
What's that?
He was yelling at me about food.
I was not yelling at you about food. I was discussing the fact that you should not have any in my class because you're not supposed to be eating in here.
It's gonna be back to
The topic was food yesterday.
And the topic of this whole unit is food, so get used to it.
I'm
Hello,
gonna get
Jennifer.
hungry.
Yes, Kayana, what can I do you for?
Can I get a loaner?
Can you get a what? A loaner what?
computer.
I don't have one. Has it been time?
Is it 7:40?
I don't know. You tell me. There's a clock on the wall up there. Go ahead and read it for
Less
me.
than a minute.
Then I guess you can't go.
It's 7:40.
Almost 7:40. Almost.
How are you guys going to survive in the real world if you can't read something as simple as a clock?
That's weird. I just can't see from back there.
So that makes me feel even better that you're sitting in the back of the room, but you can't see the clock. I imagine this is just a blobby blur to you.
Yeah.
Perfect. Please sit in the back of the room then where it makes sense.
Yeah, it makes sense, doesn't it?
No, it
All
doesn't.
the other seats are full. Oh, except for
Right
ours.
there. Right. 2 in the front row.
Someone sits next to you.
No, someone doesn't sit next to him unless they get here.
It's every other day.
Oh, that's right. You guys are on your every other day schedule still.
Well, but at least one is here every other day.
That is true. One is here every other day. So between the two of them, they get the whole class.
Yeah.
Yeah, excellent. Okay,
Oh my God.
so again, ladies and gentlemen, our three definitions. Energy is the ability to do work. Work is when you apply a force. A force is a push or pull. But in science, to do work, the object has to move. I push against this desk. While I am using energy, I'm not doing any work because the desk doesn't move. Okay? And then, again, force is simply a push or a pull. Now, these are 6 different kinds of, or 6 different forms of energy, ladies and gentlemen. Do I need to approve it?
Yeah, I think so. It says request passed.
Go. Okay? Now, thermal energy is heat energy, ladies and gentlemen. So anything that would give off heat is a type of thermal energy, ladies and gentlemen. Come on back here, cursor. Okay, so example, sunlight, fire, match, friction, anything that causes heat. Chemical energy is energy that is stored in the chemical bonds of something. So think about this. Anything that you can burn has chemical energy in it. Why? Because you can transform that chemical energy into heat. Batteries have chemical energy in them. Why? Because they can be used to power your computer, to power your phone, things of that nature. Okay? So the food that we eat is chemical energy. Why? Because it gives us the energy we need to get through the day. Okay? Nuclear energy is caused by the splitting of an atom. Breaking apart of an atom into 2 or more smaller pieces. That is what happens in a nuclear bomb. When you do that, you give off a great deal of energy. A lot of energy, ladies and gentlemen, from a very small amount of material. Electrical energy would be anything that you plug into an outlet or anything that runs on a battery. That requires electrical energy. And electrical energy is simply the movement of electrons from one place to another. But that movement can cause you to be able to do things.
Like your power cord.
Like your power cord that's running across the room and that I'll trip over later on. Electromagnetic. Okay, electromagnetic is energy traveling as a wave. That's what it actually means. And there are different kinds of this. So radio and TV waves that operate your radio when you tune it to 101.1, 98.5, whatever station you will listen to in a car. That is going away though. Why?
Like people don't listen to the radio
People don't spend as much time listening to the radio as they used to.
because they talk.
And even like in your home, you may not actually have a radio. You may listen to it through your cell phone. Now, the one thing about a cell phone, though, is a cell phone uses the exact same signals as radio and TV waves. Slow down.
But you use Bluetooth.
That's different, though. Okay, that's different, though. But that is along this same line. A Bluetooth signal would be along those radio and TV waves, allowing one thing to communicate with another wirelessly. Okay, along with radio and TV waves, we also have microwaves. We have infrared. Infrared is what remotes work on. We have visible light. And actually, the visible light we've seen is made up of the colors of the rainbow. Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv, it's called. All of those are forms of electromagnetic radiation. But so is ultraviolet, which causes you to get a tan or a sunburn in summer. So is X-rays, which can be used to see the bones inside your body. And so are gamma rays, which can be used to kill cells in your body and fighting cancer and things like that. And then there is mechanical energy. Mechanical energy is any energy that something has because of its kinetic and its potential energy, and a combination of the two. Then we got into talking about kinetic energy. And we said kinetic energy, an object needs to be moving. An object has to be moving to have... I'm sorry, I never heard her knock. Sorry.
Okay.
Never heard you knock.
I can listen from the left.
Kinetic energy is energy of motion. An object must be moving. Now again, on Earth, we could say that any object is moving. Why? Because the Earth is always spinning on its axis. It's always moving through space. Yes, I agree with that. But if we ask if this desk is moving, what would we say?
No.
No, the desk is not moving. Why? Because from our point of view right now, it is stationary. So this desk has no kinetic energy. Now again, somebody may also point out, well, Mr. Brand, the desk is made up of particles, and those particles are always moving. You taught us that before. KMT, and all matter is made up of tiny particles. They're always moving. True. So if you look at it on a molecular level, again, they have kinetic energy. But I'm looking at the object as a whole, not moving, no kinetic energy. Kinetic energy depends on two things, velocity and it depends on mass, ladies and gentlemen. Velocity is how fast and what direction an object is moving. Mass is how heavy the object is. The formula for it, kinetic energy is equal to 1/2 the mass of an object times how fast it's moving, or its velocity squared. Again, I will never make you do a calculation with that, okay? Just wanted to show it to you. KE stands for kinetic energy. You should know that it's measured in joules. Mass is measured in kilograms. Velocity is measured in meters per second. Okay? Now, in terms of food, what unit do we use for energy? And it can be converted into joules, and joules can be converted into calories. They're measuring the same thing. So it's kind of like if you measure distance in meters, you could also measure it in feet. Okay? And you could convert from one unit to another. What's another way of saying a dollar with only one kind of money? What's another way of saying $1 having only one kind of money?
Changes.
What?
Changes.
You got to be more specific. What? 4 quarters.
How many pennies?
A buck would be the same as a dollar.
How many
4
pennies?
quarters.
How many pennies?
100 pennies.
10 dimes.
10 dimes. All of those, even though they are different kinds of money, total up to be the same thing. Well, when you're talking about energy, you could measure it in joules. You could also measure it in calories, and you could convert between the two. Okay? I'm not going to ask you to do that, but we could convert between the two. Then we did this little activity, ladies and gentlemen. Now, hopefully in here, what you put was which of these was the easiest and the hardest to stop or the hardest to get going. Okay? Was it easier to move the heavy mass, the heavy book, at the same speed as the light mass? Now, hopefully you realized which one of these was the easiest to move. Say it. The one with the lightest mass. Okay? All 3 of these objects moving at the same speed. The light notebook was the easiest to stop. The heavy CRC book was the hardest to stop. Another way of saying that, or another way of translating that for us, is if something has more kinetic energy, it is harder to stop. Okay? So Jennifer and I are running a race. I know, unrealistic, but we'll do it. We are going at the exact same speed. Again, I know, unrealistic. Jennifer could never keep up with me. Anyway, we are running at the exact same speed. you accidentally walk out to the end of the track where we are about to finish the race, and you realize, oh my gosh, I'm going to get hit by one of these two people. Who do you want to get hit by? Why Jennifer? She has a smaller mass. She is going to have less kinetic energy than I have because she has a much smaller mass. Thank you for being so kind and putting it that way. She has a much smaller mass than I do, which means that if I hit you, it's going to hurt more than if she hits you. Okay? Just because, even though we're moving at the same speed, she has a lot less mass than I do. So I have more kinetic energy. We learned that yesterday. The second part said, all right, now we're going to hold the mass constant. Okay? Now we're going to hold the mass constant. Now, when we take the same mass object and send it flying at you quickly versus a medium speed versus slow, which one of these was the easiest to stop? Which one of these was the easiest to send across the table?
The easiest was the most velocity.
That was the easiest? Really? That was the easiest to stop, was the one with the most velocity, the one that was moving really fast.
The notebook was the easiest.
But here, we didn't change the mass. So we used either the notebook, we used either the textbook, or we used the CRC book. Okay?
You're saying how difficult
So-
it was at the start?
Catch. Ready? Gonna be at you a little faster. Ready? Okay, slow. Fast. Good hands. Good job, Mariana. Way to back her up. Which one is easier to stop?
The slow one.
Yeah. Why? It has less kinetic energy. The faster the object is moving, the more kinetic energy it has. So you're playing softball and the pitcher is pitching really fast and they hit you. Gonna hurt a lot, right? You're playing softball and some little kid is tossing it underhand very slow to you. You get hit by it, you're like, oh my gosh, you're killing me. No. Right? Because the faster the object is moving, the more velocity it has. I take a bullet and I throw it at Kevin, he's probably not going to be too worried. Now we shoot it out of a gun at Kevin, he's probably going to be fearing for his life. Bullet has the same mass either way, right? What's the difference? No, same bullet. But how fast it's going. How fast it's going. A bullet traveling at a slow speed is not going to hurt you. One traveling at an incredibly high speed may go right through you. Okay? So again, kinetic energy differs depending on those things. Then, ladies and gentlemen, we had gotten to this slide here where we said, okay, if the velocity increased, the kinetic energy increased. If the velocity decreased, kinetic energy decreased. So what kind of relationship is this between these two things?
Direct.
That is a direct. Now remember, this is the difference between chemistry and conceptual chemistry. We are dealing with the concept, with the relationship of these two things. We're not dealing with it mathematically. Okay? So my expectation is that you know that velocity and kinetic energy are in a direct relationship. Meaning if the object is moving faster, it's going to have more kinetic energy. It's going to have more kinetic energy. So a roller coaster going down the first hill, what happens is it goes further and further down.
Faster and faster.
Okay, which means what for its energy? Goes up and up. Now the roller coaster comes to a loop and it starts going up the loop. As it goes up, what happens to the roller coaster?
It slows down.
It slows down. What happens to the kinetic energy? It goes down as well. Can't say it slows down. We can say it goes down because kinetic energy is an amount, a number. Okay, it's getting less. We can say it's slowing down when we're talking about the velocity though. Okay? All right. So, if you sent the heavy book across the table at the same speed as the light book, what happens to the kinetic energy if the mass goes up? Kinetic energy? Really? So a kid rolls a little toy truck at you. Do you get out of the way? No, a big dump truck coming down the road, coming at you at the same speed. Do you get out of the way of it? Yeah, why? It has more what? Mass. Moving at the same speed, but more mass. What does that mean?
That the velocity is like-
No. The velocity is the same. The only thing I'm changing is the mass. The only thing I'm changing is the mass. Are you volunteering? Thank you. You're volunteering. Awesome. Excellent work, ladies and gentlemen. He's volunteering. Okay, you ready?
Sure.
You ready? You volunteered for this. You all heard him, right?
Yes.
Now, if I do the same with this book, which one's going to hurt more?
We're heavy.
Why? They're moving at the same speed. They're both being pulled down by gravity at the same speed.
The heavy one will hurt because of
Thank you.
heavier.
The heavy one will hurt more, meaning the heavy one has more what?
Mass.
Okay, but also more kinetic energy. Thank you. Kinetic energy. Thank
I
you.
would have just dropped the book on his head.
That's why you're not teaching the class. So mass goes up, kinetic energy goes up. The roller coaster at the top of the hill, as it goes down, its kinetic energy is increasing, correct?
Yeah.
Two roller coasters, side by side, going down the hill at exactly the same speed. Do they have the same kinetic energy? Two roller coasters, cards. A dueling roller coasters where they're two on the track at the same time, going down the hill.
Does it matter how much, like, the mass of people are?
That's exactly what matters, right? One has a bunch of third graders in it. One has a bunch of offensive linemen from the Kansas City Chiefs in it. Which one's going to have more mass?
Kansas City Chiefs.
Okay, which means it's going to have more what as well?
Velocity.
No, more kinetic energy. Remember, we said the velocity was the same. Okay, so Jennifer and I run that race. The velocity is the same. You're going to get out of my way. You're going to get run over by Jennifer because it's going to hurt less. Okay, so therefore, if mass decreases, kinetic energy decreases. What kind of relationship? That is also a direct relationship, ladies and gentlemen. So it doesn't matter if we're talking about mass. Doesn't matter if we're talking about velocity. They are both in a direct relationship with kinetic energy. So if we increase either one, it's going to go up. Now, there are times where you cannot increase the mass of something. Why? How do I make this heavier? You can. The mass of it is the mass, right?
Right.
I mean, if you get on a roller coaster, your mass is your mass. You cannot change that, correct?
Correct.
Now, maybe you could put more people on the coaster or fewer. But remember, an object, you can't really change its mass normally.
Right.
So how do you change its kinetic energy?
The speed.
By how fast it's moving. By how fast it's moving. So sometimes it's realistic to change the mass of something. How many people are on the roller coaster? Sometimes it's not. This object, you're not going to change its mass. You're not going to change the mass of this book. Okay? Yes, some smart aleck would say, well, Mr. Brad, I'm going to rip the pages out of it. Okay, well, then you're changing the book, too. Okay? So, keep that in mind. All right, so there is a second type of energy, ladies and gentlemen, and this is potential. And please understand, kinetic is separate from potential. You can't have both. You can have neither. Or you can have some of each. Okay? Potential energy is energy that is stored or energy of position. Can you give me an example of potential energy? Like these boxes sitting up on the shelf. These boxes sitting up on the shelf have potential energy. Why? Because they can fall. How about this desk?
Yes.
Why?
Oh.
Because we're sitting on it.
What?
Because we're sitting.
It doesn't matter if you're sitting on it. I'm asking about this desk right here. Does it have potential energy? Can it fall any lower in this room?
No.
No.
Yes,
Now,
it is.
there's someone who will say, well, Mr. Brand, we're on the second floor of the building. What would happen if the floor would collapse? I'd want to be in a different room. But what would happen if the floor would collapse? It could fall down, right?
Right.
Then in that case, yes. But from our perspective right now in this room, does that desk have potential energy? No.
No.
Give me some other object that has potential
The
energy.
posters.
What?
The posters.
The posters. Why?
Because they could fall off the wall.
They're hanging up high, they're above, they could fall down. Give me something else. What? Why? Okay, so the computer is sitting up high on the desk, it could fall. Give me something other than an object that could fall. How else could you store energy?
Oh, like in that file cabinet, like you can store stuff inside
But
it.
that's different. Yes, you could store stuff in there, right? Well, again, if you jump and go into the air, you could come back down, okay, but I'm not jumping for you. Why?
I was thinking you could just add force and then
Okay, but again, you're talking about position. I'm not disagreeing with any of those things. This object could fall. These objects could fall. But I want to know potential energy, stored energy another way. How does this have stored energy in it?
The
And
battery.
don't say because you could drop it, Mr.
The
Brand.
battery.
The battery. The battery in here is stored energy.
Just like
The
your
battery
Chromebook.
in there is energy that is waiting to be used. It's stored energy.
Just like your Chromebook.
Just like a Chromebook. What? Very good. Thank you. Stretch this out. It goes back on its own. That's stored energy. I'm storing the energy up now, letting it go. Yes. Very. Okay. So again, we can store up energy in a lot of different ways. Yes.
Would like a basketball be an example of stored energy?
A basketball would be an example of stored energy because when you bounce the ball and it hits the ground, what happens to it?
It comes back.
Why? Why? How does it store it? How does it store it? What does a basketball do that stores energy? I got news for you. A basketball can do it, a bowling ball can't.
Because of the air in the ball.
What it's made out of?
Okay, two things. One, what it's made out of, and two, what's inside it. But what will a basketball do that a bowling ball will not?
Bounce.
Why?
Made out of rubber. And like a bowling ball is made out of whatever a bowling ball is made out of.
Isn't it like when the ball hits the ground and like flattens and then it just goes back?
When the ball hits the ground, it deforms. Changes its shape just for a second. We can hardly see it. We really can't see it. But this stores up energy that when you release it, boom, it goes back to its normal shape and comes bouncing up. Why doesn't a bowling ball do that? It doesn't deform. It doesn't deform. Okay? Now, maybe the ground gives a little bit and you get a little bit of bounce, but the bowling ball doesn't deform. Does a soccer ball deform? Yeah. Does a baseball?
No.
Yes.
Really?
If you ever look at a picture of a baseball when a bat hits it, it compresses and then it releases and goes the other direction. Even a golf ball does that same thing, even though it doesn't look like it should. People are like, well, a golf ball is kind of like a bowling ball. No. Golf balls can compress and then release and take that energy with them. So when we say stored energy, ladies and gentlemen, there are a few ways that we can store it up. There are three kinds. There's one gravitational, and that's what we were all talking about at the start. Kevin, when you said this could fall off to the ground, yes, absolutely. That's gravitational potential energy. If an object can fall, that's gravitational potential. Now, this object cannot fall. Why? It's already at the slowest point. It's on the ground. All the objects on your desk could fall. They all have potential energy. Any object that is above the ground level can fall, has potential energy. Second kind, though, is elastic potential, and that's what we're talking about here. That's what we're talking about here. This is elastic potential energy. Inside here, there is a spring, and as I pull this out, that spring winds tighter. Why? So that when I let go, it will come back. Okay? The ball deforms so that it can bounce back up. Pull a bow on a bow and arrow. You have deformed it. As soon as you let go, that bowl goes back to its regular shape. The arrow goes flying. That is what we mean by elastic potential, based on stretch or being deformed. Think about springs, okay? Chemical energy. That is the third type. So the battery in your computer, the battery in your cell phone, the food that you eat, the gasoline in a car, those are all chemical energy. Yes, sir.
Does the suspension on a car
Would be elastic. The springs. Yes. Yes. So as you go over a bump, those springs compress. When you come off, they go back up to their normal shape. That is elastic potential energy. Anytime something changes its shape and then goes back. Now, changing its shape and then goes back. If I hit this door jamb with a hammer, it's not going to go back to its shape. What's it going to do?
Stay there forever.
What? It's going to dent it. That's not the same thing. Okay? Got to go back to its original shape. All right. The easiest one of these three to talk about, ladies and gentlemen, is this one, gravitational potential energy. Okay? Because, again, we think of these boxes sitting up high, the things on the desk. What determines how much potential energy that box has? What? How high it is. How high it is. So the higher up the object is, the more potential energy it's going to have. What else? It's mass. The heavier the object is. Now, this box is empty. You get hit in the head by it, it's going to hurt. Not badly. This box here has a bunch of models in it. It's heavy. You get hit on the head by that, you're going to know it. Okay? You're going to know it. So again, depending on two factors, depending on mass, how much matter the object has, and depending on height. Now, technically, there is a third factor, but you and I cannot control it. Anybody know what the third factor is? What causes those objects to fall? Nope, not their height.
Gravitational.
Gravity. Gravity also affects potential energy. But since we all live on Earth, and since we all will probably never leave Earth, we all live under the same gravity. So we can't change that. We cannot change that. Okay? We cannot change that. If you went to another planet, if they colonize the moon and you get to live there when you're 60, go ahead. Congratulations, you have found the greatest weight loss clinic in the world, because you will weigh 1/6 on the moon what you do here on Earth. Meaning if you're 180 pounds, you'll weigh 30 pounds on the moon. If you're 120 pounds, you'll weigh 20 pounds on the moon. Okay? You'll weigh 1/6 of what you do. Which means when you get there, you should be able to jump 6 times higher on the moon than you can on Earth. Because there's 1/6 the gravity. Okay? The problem is, if you lived on the moon for a long time, what would happen if you came back down to Earth? What? No. You'd be very weak. Why? There's 1/6 the gravity. When you lift an object on the Earth, you've got to lift it at 6 times what it would be if you lifted it on the moon. Okay? All right. So, ladies and gentlemen, again, the formula for potential energy is similar to the one for kinetic. It involves mass, but then instead of velocity, it involves gravity and height. Kinetic energy or potential energy is measured in joules, same as kinetic. Mass is still measured in kilograms. Gravity is 9.8 meters per second squared. Can't change it. You cannot change it. That never changes. All objects fall at exactly the same rate. And height is measured in meters. Okay? Height is measured in meters. So, questions? No? Good. So let's go take a look at this. So you're going to use the same 3 books you did yesterday. But we're going to change what we're doing. In the first part, again, our mass is going to be the variable, meaning you're going to work with the CRC book, the notebook, and the textbook. Okay? What is going to be the same is going to be the height. So you are going to partner up. Faith, come here. Stand right here. Put your arms out in front of you. Okay. Catch this. You ready? No, but yeah. Good, good. Ready? Okay. So I'm going to take and I'm going to switch the book, hold it at the same height I was holding it at about face head. I'm going to drop it and she's going to catch all three. And she's going to judge which one was the easiest to stop, the hardest to stop, and the medium to stop. Okay? Then switch and have your partner do it. Okay, go ahead and sit down. Okay? So that is the first part. The height is constant. The mass, the variable. Again, which one is the easiest, which one is the hardest. Now for part 2, ladies and gentlemen. All right, who's going to help me with that? Kayana, can you help me with that? Good. Come on back here. Okay. Now again, I'm only going to pick one of the 3 books because I'm going to keep the mass constant, but I am going to change the height. Okay, so you ready? Okay, ready? So we do one height, we do a second height, then we do a third height.
Oh.
Ready? No, I'm serious. Get over here. Ready?
Yeah.
Okay, and you're going to determine which one is the easiest, hardest, and in the middle
Do
to
we
stop.
have to stand on the table?
You don't have to, but you need to make sure you have 3 very different heights. So, what are you standing around for? Let's go get that one. Don't drop my books on the ground. Catch them. Catch them. Don't drop the books on the ground. You can drop them from different heights. Don't drop them on the ground. Catch them. But right now, we need to get to work.
I'm doing instructing because I have a lot of junk.
Well, I know, but just not the time right now. Okay? Go, go, go. Go ahead. Don't kill yourself climbing up steps to get on the table, please.
Actually, I felt like
Great. That makes me feel very confident having you up there, man. Now remember, you did the second part of this. You did the first part. And that's fine. You can do them in any order, but make sure you put those results in the second part where you chose to use the heavy book. Okay. So you climb up it on the steps, but then you jump to get down. The steps were shaky? What?
Maybe he felt shakier.
Okay, we'll go.
Yes.
The whole ladder moved once you got down.
I got news for you. Everything made out of metal in this room is a little rusty.
It's not even on it. It's not even on the floor, Mr. Brown.
Well, it does because it's made so that right now you can wheel it around. But when you step on it, it goes down firmly onto the ground. That's okay. That's okay. Let's get things done so that you can move it around.
I'm afraid to go on the table. I'm afraid.
Then don't. Just do it. Do it 3 heights. You can do up here, here, and down here. Don't do it if you don't want to. Because I don't need you to fall and kill yourself. Correct. Which one was the easiest to catch, hardest to catch, and somewhere in the middle? You have to ask her because she called it. Okay. So put hardest, easiest.
You can come up on the table and I'll pick it. It's really even.
Okay, well, just put it down and let's move on to the next part of the lab. Remember, you're just ranking them. Which one was the easiest? Which one was the hardest? Which one was somewhere in the middle? So that's all you got to do is rank them, ladies and gentlemen.
Very clean, Mr. Brand.
Why are we going up there with a different Okay, so for the height, you went up there and you compared. Okay, that's fine. Go ahead.
Isn't the more mass?
Heavy
What height?
The more mass it has.
Yes, but here, if you drop any object from here to here, it's going to be at the same speed. So let me see this. Let me the light one. I hold them here and drop them. Which is ground first. Oh, they both hit it at the same time, right? So what does that tell you about their speed? Their speed is the same. So that is a good thought. But objects fall at the same rate because of gravity. When you drop two objects at the same height, they should hit the same. Assuming I got it at the same time. But in reality, it's not like you hear one thud, you don't hear the thud. Meaning they're hitting the same. Okay?
What do you think?
Okay?
They want the textbook and then it went the notebook.
They felt the same.
Yes.
They felt the same.
So this is chemistry.
I know. I know they
Try it.
But right now, we're talking about energy. Because in chemical.
Maybe to help you, Pat.
Think about the.
Yeah, that would be cool.
Remember we took that aluminum oil and mixed
Yeah,
it with that.
you were like that word.
Yeah, I was okay.
It gave off
You were like right on top of her.
But it also gave off. Gave off heat.
See, you catch.
Gave off energy. That radiation gives off energy, just like we're talking about here. That energy was potential energy in the body. That when you rearrange what's in there, sometimes you release that energy.
I gotta give her a warning before you drop that one. Because she's got a little long.
Just getting through the energy part of this right there. All right, let's get done, ladies and gentlemen, and then head back to our desk once you're finished, please, okay? Make sure you do the summary part. Okay? When you increase the mass, what happened to the potential energy and how do you know it? And again, you could say because it was harder to stop or easier to stop. Okay? When we increase the height, what happened to the potential energy? Did it go up or down? And again, we can say that because it was easier or harder to stop. So you're using your perspective from the lab to justify what you are saying, which is absolutely fine. You're collecting qualitative observations, how something feels. No numbers here. Thank you.
I'm doing some of that for a class. I wanted to do for the math, but I don't know if the students will allow it to be asked.
Yesterday,
Somehow.
in the school, and like I haven't had gyms.
Why? I don't drink coffee after I leave home in the morning. Why are you looking at me like I'm crazy?
Wait, did you say you don't drink coffee?
I have 1 cup a day at home in the morning. After that, no. Why are you looking at me like I'm crazy?
What time do you get up?
I get up at 4:30.
I get up at 6 in the morning every morning.
Do you?
By the time you get to school, I'm already getting up. By the time he gets towards 6 o'clock, I just get up.
Okay.
You do? I can't even wake up.
I get up at 6:30. I get a half hour.
First of all, I think you are physically capable of getting up at whatever time you want.
Okay, I get up
a half hour earlier than you.
I have an alarm at 5:30, 5:45.
Oh my God, you're
6:15, and 6:30.
Well, that's absolutely ridiculous. Sure you can. Okay, so ladies and gentlemen,
go back to bed.
let's summarize what we just learned. Okay? Again, we're going to change the mass. We're going to use the light book, the medium book, and the heavy book. What we are not going to change is gravity, obviously, because we cannot. And we are not going to change the height. So we dropped it from the same height each time. Which book was the hardest to catch?
The heavy book.
Okay, the heavy book. So meaning as mass increases, it's harder to catch the heavy book because it had more what? Not kinetic energy, potential energy. Okay? So again, if mass goes up, the potential energy goes up. You walk underneath this box, as the empty one hits you on the head, not a big deal. The full one hits you on the head, you may get knocked out. Okay? The more mass, the more potential energy something has. Which means if mass goes down, what happens to potential energy?
Goes up.
It what? So it decreases. Okay? You can't go up when mass goes up, and you can't go up when mass goes down. That makes no sense. One or the other. So what kind of relationship? Again, it's a direct. I would love to give you an inverse relationship, but I can't because these are all direct. Okay? So in other words, it doesn't matter whether you're talking about kinetic or potential energy. If the mass increases, what happens to kinetic? And what happens to potential? Yeah. So the heavier the object, the more energy it is going to have no matter what, whether it's kinetic or potential. Okay. So the next slide, now we are leaving mass and gravity constant. Same book each time. Low height, medium height, high height. What happens as we increase the height? When the person stood on the desk and dropped it, was it easier to catch or harder to catch than when they held it just above your hands? Okay, so therefore, if the height increases, what happens to potential energy? It increases as well. And if the height decreases,
Right.
potential energy decreases. What kind of relationship? Again, a direct. Not everything is like this, but for these, this is the way they are. Okay? Questions? Yes.
The last slide, was it direct relationship?
Yes, it was a direct.
Okay.
So when you're done, it should have a direct at the bottom. Get rid of the other one, please. Okay? Questions? All right. The law of conservation of energy says that energy cannot be created or destroyed. It can be what? Transferred or changed. Okay? Energy cannot be created or destroyed. It can be transferred or it can be changed. So, what kind of energy does this ball have right? Oh, wait. Now. Why? Okay, it's not moving, so it can't have kinetic. It's got potential, right?
Right.
So, potential energy here compared to here. What has happened to the potential energy?
It decreased.
It decreased, because we said height changes the potential energy. The higher up, the more potential energy. The lower down, the less. So when I drop this ball, what kind of energy does it have as it's falling? Kinetic, because it's what? Moving. But also, all the way down, it still has what? Potential. Where did the kinetic come from? I understand that, but where did this ball get kinetic energy from if right now it only has potential?
Because when you drop it, like, it's a good, like, I don't know how to explain it.
Okay, well, let me ask you this. I'm going to use this desk as our baseline, our bottom. Okay? Here, potential energy. Give me a number. Let's say 100. Halfway down, how much potential energy? 50. At the bottom, how much potential energy? 0. 100, 50, 0. Right? So as it's falling, what's happening to the potential energy?
It decreases.
Decreases. Now, kinetic energy. The mass doesn't change, so the only thing that can change the kinetic energy is
For potential energy.
what it's moving.
Fast.
Fast. Speed here, 0.
Right.
Just as it hits down here, that is what is it's going to be moving? So let's call it 100. 0, 100, halfway in between. 50. Because it hasn't gotten as fast as it's going yet. So you'll notice 0, 50, 100 for kinetic, correct?
Correct.
Potential 100, 50.
0.
Where'd the potential go? Where'd the potential energy go? It transferred into the kinetic. It became the kinetic energy. Halfway down, we've lost half of the potential, right?
Right.
It went to kinetic. All the way down, we've lost all the potential. Now it's all what? Kinetic. Now it bounces back up, correct?
Correct.
Starts moving back up. Okay? At the bottom, how much potential? 0, 50, 100. Now what's going to happen to the speed as it comes back up? Okay, so kinetic, what do we got down here? 100.
0.
One is changing to the other. That is all that's happening. Imagine a kid on a swing. Swinging back and forth, right?
Right.
At the end over here, what does he do right before he comes back down? He stops. What does that mean for his kinetic energy? It's all potential. At the very bottom of the swing, can he go any lower? So what does that mean for his potential? 0. But that's also when he's maximum what? Kinetic. So these things can change. It can go from one thing to another. What does the gasoline in your car engine use to do?
Go.
To move the car, right? So gasoline would be what kind of energy?
Potential.
Potential, but more specifically chemical, correct?
Correct.
When the car is moving, though, it has what?
Kinetic.
Kinetic or mechanical energy. So we could take chemical energy and make it into mechanical. Yes.
This is going to be kind of a weird.
Well, let's get to it. Come on.
So when a baseball pitcher is pitching the ball, right?
Yep.
Pitches a knuckleball. The ball doesn't really spin that well. It just,
Okay.
what kind of energy would the ball?
Is the ball moving?
Yeah.
So that means it has.
Kinetic energy.
Okay, is the ball above the ground?
Yeah.
Then it has.
Potential energy.
Yeah. Kinetic potential are the simplest energies to talk about. Okay? They're the simplest to talk about. You want to get more specific? We could talk about thermal energy. We could talk about electromagnetic energy. We could talk about chemical energy. Kinetic potential are the easiest because if the ball is above the ground, what does it have? Potential. If the ball is moving, what does it have? And it's that simple. If the object cannot fall, if the object is as low as it can be, it has no potential. If the object is not moving, it has no kinetic. Simple. Okay? That's what kinetic and potential are. Now, a knuckleball, the reason it moves the way it does is because it's not spinning. That's a whole different thing, though. Whole different thing. Okay? Good. Good question. So you can go from kinetic to potential or kinetic or potential to kinetic easily. A kid on a swing, swinging back and forth, throwing the ball up into the air and letting it come back down. We're transforming kinetic to potential and potential to kinetic all the time.
Find the remaining angle measures.
The remaining angle measures. Oh my gosh, that sounded like math. Electromagnetic can become thermal. Sunlight gives off heat. Sunlight is electromagnetic radiation, ladies and gentlemen. And it gives off heat. One becomes the other. Nuclear can become thermal. We use a nuclear reaction to make electricity in a power plant by heating water with the nuclear reaction. Heating water. And then the water turning into steam and spinning a turbine takes mechanical energy and makes it into electrical energy. You can change all these different types of energy from one to another. Okay? You could change them all. Any change is possible. What happens to the food you eat? What's it get used for? How? In what way? Okay, but I agree with you. I completely understand it. What kind of energy do you use the food for? That is chemical energy, the food, yes. But then what do you use it for? Moving! So you're converting chemical energy into mechanical energy because you're moving. Now, also, your body needs to maintain a certain what? Starts with T, ends with temperature. Very good, temperature. Which means some of the energy goes to what? Heat, thermal energy. Chemical energy to thermal energy. Good. Okay? So we need these things. You plug your cord into the outlet, you're taking electrical energy and doing what to your battery? Which makes what kind of energy? Chemical. All these transformations happen. You plug a blender into an outlet, you take electrical energy and make it into mechanical as it spins. Those are energy transformations. The one thing you can't do, though, is we can't get any more energy out than we started with. You cannot create more energy than was there. You could transform it. You can make it into a different kind. You cannot get more than you started with. And you also don't lose any. Okay? All right. Give me an object that has just gravitational potential energy.
A ball.
Nope, not specific enough. To have gravitational potential energy, what has to happen? What? Okay, so it has to have a height. Give me an example. What? The tissue box.
I was gonna say like up on the shelf.
Okay, give me an example of the books or the boxes up there. The containers of water in the back. By the way, which container of water in the back has the most potential energy of the four?
No,
Why that one over there?
because it's more full.
Very good. So not only can we compare them, but we can say, okay, that one has the most potential energy. Why? Because they're all at the same height, but that one has the most water in it. Good, 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 good. Give me an object with just elastic potential energy.
Your ID lanyard.
My ID lanyard. My ID lanyard. A spring. Hey, guess what? You'll find those in most pens. There's a spring in there.
And mechanical pencils probably too.
Nope, not mechanical pencils. Mechanical pencils do not have a spring in there because when you're done with your mechanical pencil, you have to push the button and you push it back in. Not a spring putting it back in. Just potential energy or chemical potential. Give me an object. Give me an object with just chemical potential energy. Yeah, because there's what in here? Don't say juice. There's calories in here. Calories in here. What are you drinking?
Water.
Chemical potential energy? Why? No calories in water. No calories in water. The food has to have calories in it to have energy. Object with just kinetic energy, no potential. Now think about it. Kinetic means it has to be.
Moving.
No potential means it must be.
Not moving.
No. Okay. Potential means above, right? So when would you have no potential?
Whoa.
when you're on the ground. So give me an example of something with kinetic energy and no potential.
The wind.
More specific. Doing what? A moving car going over a bridge? Going over a bridge, what would the car have? Why? Because it could fall off the bridge. So the car's got to be moving where? At the lowest possible, right? So a ball rolling across the floor here, okay? At its lowest level, but moving. Okay? How can you have both kinetic and potential? Okay, more specific. More specific still. Okay, rolling on the counter, yes. But any object that is moving, and for potential you have to have height. Give me an object that is moving and has height. A pitched baseball. More specific. A flying airplane. Yes, not flying on the ground, not rolling while it's taking off, but flying through the air. You bet, as long as it's what? As long as it's moving and you're spinning around, you betcha. Okay? Any object that's moving and has height, a thrown ball, a thrown frisbee, a kicked soccer ball that's flying through the air. Got to be flying through the air, though. Your plane, you got to be a little more specific. The plane might be sitting on the runway, not moving. Doesn't have either kinetic or potential. Plane's got to be flying through the air. Any object flying through the air has both kinetic and potential, because you got to be moving and you got to be above the ground. Good. Questions? All right. All right. I had hoped we would have a little bit more time for this, ladies and gentlemen, but in your Google Classroom, and I will give you a little bit of time tomorrow to work on it. In Google Classroom, ladies and gentlemen, there is an assignment for you, and it is the energy worksheet. Again, this is the stuff that is going to be on the quiz on Friday. I do not grade homework on you. You don't do this, well, it's not going to affect your grade until you get to the quiz on Friday and you suck on the quiz. Why? Because you didn't bother to look up what these terms mean. So here's your word bank, ladies and gentlemen, that goes with these questions. Okay? A way of creating energy through fission, splitting of atoms, heat or the vibration and movement of atoms and molecules within substances, energy of negatively charged electrons, energy traveling as a wave such as X-rays, gamma rays. The word bank is up above that has it. Don't you dare do that, please, because you're plugging into my cord and I don't want my cord coming off the wall there. Okay, so please get up and do that next time. Okay, on this one, 3 balls, 3 objects dropped from the same height of 10 meters. Which one of these has the most potential energy, the medium potential energy, and the least? Look at what is different about them. Here, ladies and gentlemen, what kind of energy does it have? A dog running, a cookie, a stretched hair tie. Do they have gravitational potential? Do they have chemical potential, elastic potential, or kinetic energy? Which one do they have? So, by the way, a dog running probably is running where? On the what? On the ground. So what does that mean? Good. Kinetic energy, no potential. Go with the most obvious one. Some of these, if you look at them and examine them, they might be more than one kind of energy. Go with the most obvious, please. Okay? Go with the most obvious, please. And then, time to recall some biology or look up these answers in Google. You got those 4 to do. And then here's that picture. This is either a kid on a swing or a ball on a string moving back and forth. Okay, where do you have the most kinetic, the least kinetic, and the medium kinetic? So E compared to C compared to B. Which one of those has the most? Which one of those has the object's mass is not going to change here. Okay, and then describe those on the bottom. Okay, Now, tomorrow I will give you a little bit of time to work on this as well. It's due by the end of the day tomorrow. Questions, ladies and gentlemen?